You are mostly nothing. Your body, your bones, your brain. 99.9% empty space. Let that sink in for a moment. If you could remove all that emptiness and compress just the actual stuff you're made of, you'd be smaller than a grain of sand. All of you, every memory you have, every thought, every cell in your body, condensed down to something you could barely see. So here's my question. Why are you solid? Why don't you fall through the floor? Why doesn't your hand pass through the table when you touch it? The answer is going to change everything you think you know about reality. Right now, as you're watching this, you think you're sitting on something solid, a chair maybe, or a bed. You feel it beneath you. It feels real, dense, substantial, but it's not. That chair is mostly empty space. So is the floor beneath it. So are you. And the sensation you're feeling, that resistance, that solidity, it's not what you think it is. It's not two solid objects pressing against each other. It's something far stranger. It's a quantum mechanical force, a consequence of the wave nature of matter, a rule that says certain particles cannot occupy the same state at the same time. You are being held up by a law of physics that operates at scales so small you cannot see them, cannot touch them, cannot directly experience them. And yet, it's the only reason you exist. By the end of this video, you're going to look at your own hand, this thing you've lived with your entire life, and realize you have no idea what it actually is, because matter is not what we thought it was. Let's start from the beginning. The word atom comes from the Greek word atomos. It means indivisible. Around 400 BC, a philosopher named Democritus had an idea. He said, if you keep cutting matter into smaller and smaller pieces, eventually you'll reach a point where you can't cut anymore. The smallest possible piece, the atom. He was right, sort of. For over 2,000 years, the atom remained just an idea. No one could prove it existed. No one could see it. It was just a useful concept. Maybe matter is made of tiny, indivisible pieces. Maybe. Then, in the early 1800s, a British chemist named John Dalton started doing experiments. He noticed something interesting. Chemical reactions always involve specific ratios of elements. If you wanted to make water, you always needed 2 hydrogen atoms for every 1 oxygen atom, always. No exceptions. This suggested that matter really was made of discrete units, atoms. By the late 1800s, scientists had accepted that atoms were real, but they still didn't know what atoms were made of. Then, in 1897, J.J. Thomson discovered the electron. He was experimenting with cathode rays, beams of something shooting out of a negatively charged electrode in a vacuum tube. He found that these rays were deflected by magnetic fields, which meant they were made of charged particles, particles smaller than atoms. So atoms weren't indivisible after all. Thomson proposed a model. He called it the plum pudding model. He imagined the atom as a blob of positive charge with tiny negatively charged electrons embedded in it, like raisins in a pudding. It was a nice idea. It was also completely wrong. In 1911, Ernest Rutherford did an experiment that changed everything. He took a thin sheet of gold foil and fired alpha particles at it. Alpha particles are helium nuclei, positively charged, fast-moving. If Thomson's model was correct, the alpha particles should pass through the gold foil with only slight deflections, like bullets passing through pudding. But that's not what happened. Most of the alpha particles did pass through, but a small number, about 1 in 8,000, bounced straight back. Rutherford was stunned. He later said it was as if you fired a cannonball at tissue paper and it bounced back and hit you. The only way this made sense was if the atom wasn't a blob of positive charge. It had to have a tiny, dense core, a nucleus. The positive charge wasn't spread out. It was concentrated in a space so incredibly small that most of the alpha particles missed it entirely. But the ones that hit it, those bounced back. Rutherford had discovered the atomic nucleus, and he realized something shocking. The atom was mostly empty space. The nucleus was tiny, about 100,000th the size of the atom. Let me put that in perspective. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble sitting at the center of the field. And the electrons, they'd be tiny dots somewhere in the stands, or maybe outside the stadium entirely. We don't really know, because electrons don't have definite positions. Everything in between, the entire football field, the seats, the concourse, the parking lot, is empty. Nothing there. And yet, that nothing is what makes you solid. Now let's zoom in on the nucleus, because that's where most of the mass is. Protons and neutrons, each about 10-15 meters across, packed together in a dense little ball. But here's the thing. Protons and neutrons aren't fundamental. They're made of quarks, 3 quarks each, bound together by something called the strong nuclear force. And quarks, as far as we can tell, are point particles, 0 size, no internal structure. So even the nucleus, the part of the atom that actually has mass, is mostly empty space held together by forces. You're not made of stuff. You're made of forces, acting on nothingness. Let that sink in. All right, let's talk about electrons. In the old model, the Bohr model from 1913, electrons orbit the nucleus, like planets orbiting the sun. Neat, tidy, easy to visualize, and completely wrong. Here's the problem. If electrons are orbiting the nucleus, they're accelerating, and any charged particle that accelerates emits electromagnetic radiation, light. That's a basic law of physics, established by Maxwell in the 1860s. So an orbiting electron should be constantly emitting light, and as it emits light, it loses energy. And if it loses energy, its orbit should decay. It should spiral inward, closer and closer to the nucleus, until it crashes into it. According to classical physics, atoms should collapse in about 1/trillionth of a second, but they don't. Atoms are stable. They last billions of years. You're made of atoms that have existed since the beginning of the universe, and they haven't collapsed. Why not? The answer came from a Danish physicist named Niels Bohr. In 1913, Bohr proposed something radical. Electrons can only exist in certain specific orbits, not just any orbit. Only orbits with certain quantized energy levels. An electron in one of these allowed orbits doesn't radiate energy. It just sits there, stable. It can jump from one allowed orbit to another by absorbing or emitting a photon, a particle of light, with exactly the right energy. But it can't exist in between. This explained why atoms are stable. Electrons sit in these allowed orbits and don't spiral inward. It also explained the spectrum of hydrogen, the specific wavelengths of light that hydrogen emits. Each wavelength corresponds to an electron jumping from one energy level to another. Bohr's model worked. It matched the experimental data beautifully, but it didn't make sense. Why could electrons only exist in certain orbits? What was stopping them from being anywhere else? Bohr didn't know. He just wrote down the rule and moved on. Then, in the 1920s, quantum mechanics was born. Louis de Broglie proposed something crazy. Electrons aren't just particles. They're also waves. Everything is both a particle and a wave. Matter has a wavelength. For large objects, like you or a baseball, the wavelength is so incredibly tiny that you never notice it. You behave like a classical particle. But for something as small and light as an electron, the wavelength is significant. And if an electron is a wave, then it doesn't orbit the nucleus in the classical sense. Instead, it forms a standing wave around the nucleus. Think of a guitar string. When you pluck it, it vibrates. But it doesn't vibrate at just any frequency. It vibrates at specific frequencies, harmonics, determined by the length of the string. The string can vibrate at its fundamental frequency, or at twice that frequency, or 3 times. But it can't vibrate at frequencies in between. Those modes don't fit. Electrons are like that. They form standing waves around the nucleus, and only certain wavelengths, certain modes, fit. Those allowed modes are the allowed energy levels. That's why electrons can't exist at arbitrary distances from the nucleus. Only certain standing wave patterns are possible. This was the breakthrough. Erwin Schrödinger wrote down an equation, the Schrödinger equation, that describes how the electron's wave function evolves over time. And when you solve that equation for an electron in an atom, You get exactly the energy levels that Bohr had proposed. But now there was an explanation. The electron isn't a particle orbiting. It's a wave, and only certain wave patterns are stable. Now here's where things get really strange. If an electron is a wave, where is it? The answer is, it's everywhere the wave is. The wave function, usually written as the Greek letter psi, psi, is spread out over space. It has a value at every point. But the wave function itself isn't a physical thing. It's a probability amplitude. The square of the wave function, f(2), gives you the probability of finding the electron at a particular location if you measure it. Before you measure it, the electron doesn't have a definite position. It's in a superposition of all possible positions, weighted by the probability amplitude. Only when you measure it does it collapse into a definite state. This is the Copenhagen interpretation of quantum mechanics. And it's deeply weird. The electron isn't really at one location, and you just don't know where. It genuinely doesn't have a location until you measure it. It exists as a cloud of probability, and that cloud is what gives the atom its size. Now we get to the key question. If atoms are mostly empty space, why don't you fall through the floor? The answer is a principle discovered by Wolfgang Pauli in 1925. It's called the Pauli exclusion principle, and it's one of the strangest rules in all of physics. Here's what it says. No two fermions can occupy the same quantum state at the same time. Fermions are particles with half-integer spin. Electrons are fermions. They have spin 1, 2. Spin is a quantum property. It's not literally the electron spinning like a top. It's an intrinsic angular momentum. Don't ask me to explain it better than that. Nobody really understands spin. So what's a quantum state? It's a complete description of a particle. For an electron in an atom, the quantum state includes which orbital it's in, 1s, 2s, 2p, etc. Its energy, its spin, up or down. Two electrons can be in the same orbital if they have opposite spins. One spin up, one spin down. But you can't have two electrons with the same spin in the same orbital. Pauli says no. This is why the periodic table exists. Hydrogen has one electron. It sits in the 1s orbital. Helium has two electrons. They both fit in the 1s orbital, one spin up, one spin down. Lithium has 3 electrons. 2 go in the 1s orbital. The third, it has to go in the 2s orbital. There's no room in the 1s. Pauli exclusion forbids it. And so on all the way up the periodic table. Each element has a different number of electrons, and they fill up the orbitals in order. Respecting the Pauli exclusion principle, this is the structure of matter. But here's where it gets interesting for solidity. When you bring two atoms close together, their electron clouds start to overlap. And when they overlap, you're trying to put electrons from both atoms into the same region of space. But the Pauli exclusion principle says you can't have two electrons in the same quantum state. So the electrons resist. This resistance is called degeneracy pressure. It's not a force in the traditional sense. It's a quantum mechanical effect. The electrons don't want to be in the same state, so they push the atoms apart. And this is what you feel as solidity. When you press your hand against the table, the electron clouds in your hand are getting close to the electron clouds in the table. The electrons repel each other, not just because of electrostatic repulsion, though that's also happening, but because of the Pauli exclusion principle. The wave functions of the electrons are overlapping, and quantum mechanics says they can't occupy the same state, so they resist. You feel that resistance as the table pushing back against your hand. You interpret it as solidity, but it's not solidity in the classical sense. It's quantum degeneracy pressure. You are being held up by the Pauli exclusion principle, and this same principle operates throughout the universe. White dwarf stars, the remnants of dead stars like our sun, are held up by electron degeneracy pressure. Gravity is trying to crush them, but the electrons in the star resist. They can't all be squeezed into the same state, so the star stabilizes at a certain size until the mass gets too high. If a white dwarf accretes enough mass from a companion star, it reaches a limit, the Chandrasekhar limit, about 1.4 times the mass of the sun. At that point, even electron degeneracy pressure can't hold it up. The electrons get squeezed into the protons. They merge to form neutrons, and you get a neutron star. In a neutron star, it's neutron degeneracy pressure that provides support. Same principle, different particles. But if the star is too massive, above about 3 solar masses, not even neutron degeneracy pressure can stop the collapse. The star implodes. Space-time itself can't resist. You get a black hole. All of this, the stability of atoms, the solidity of matter, the structure of dead stars, comes from the Pauli exclusion principle, a quantum rule that says no two fermions in the same state. That's it. That's what holds the universe apart. So let me ask you this. What does it mean to touch something? You think you're touching the table right now, but you're not. Not in the way you imagine. Your hand and the table are both made of atoms, and those atoms are mostly empty space. The nuclei are tiny. The electrons are probability clouds. When you touch the table, what's really happening is this. The electron clouds of the atoms in your hand are getting close to the electron clouds of the atoms in the table. And as they get close, they start to repel. Because of the Pauli exclusion principle, because of electrostatic repulsion, electrons are negatively charged, like charges repel. So there's a force pushing your hand away from the table, an electromagnetic force. But you don't feel that as a force in the usual sense. You feel it as resistance, as solidity. The table pushes back. But here's the thing. There's no actual contact, no point where your atoms and the table's atoms touch, because atoms don't have hard edges. They're clouds, fuzzy, probabilistic clouds. So when you touch the table, you're really experiencing the electromagnetic repulsion between electron clouds that are getting close, but never actually meeting. You've never touched anything in your life. Not your mother's hand when you were born, not your first kiss, not the ground beneath your feet. Every interaction you've ever had with the physical world has been mediated by electromagnetic forces between atoms that never actually made contact. You are floating, always. A tiny fraction of a nanometer above every surface you think you're touching, held up by quantum mechanical repulsion. That's what solid means. All right, so atoms are mostly empty space. Fine, but they have mass. You have mass. Where does that mass come from? Good question. Most of the mass of an atom is in the nucleus. Protons and neutrons. A proton weighs about 1.67 x 10^27 kilograms. A neutron weighs about the same. An electron weighs about 9.11 x 10^31 kilograms. About 2,000 times lighter. So if you're a carbon atom, 6 protons, 6 neutrons, 6 electrons, almost all of your mass comes from the nucleus. But here's the thing. Protons and neutrons are made of quarks. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. And quarks, as far as we know, are fundamental, point particles, no size. So where does the mass come from? Well, quarks do have mass. An up quark weighs about 2.2 MeV C2. A down quark weighs about 4.7 MeV C2. If you add up the masses of the quarks in a proton, 2 ups and 1 down, you get about 9 MeV C2. But a proton weighs 938 MeV C2. So where does the other 99% of the mass come from? Energy. Specifically, the energy of the strong nuclear force binding the quarks together. E mc2, Einstein's famous equation. Mass and energy are equivalent. The quarks are bound together by particles called gluons. They carry the strong force. And those gluons have energy, a lot of energy. That energy contributes to the mass of the proton. So the proton's mass isn't just the sum of its parts. It's the sum of its parts, plus the binding energy. In fact, most of your mass, most of the mass of everything you see, comes not from the quarks themselves, but from the energy of the forces holding the quarks together. You are made of energy, frozen energy in a sense, bound into particles by forces we still don't fully understand. Let's go even deeper. What is an electron, really? You might think it's a particle, a little ball of charge and mass, but that's not quite right. In quantum field theory, the most accurate description of reality we have, particles aren't fundamental. Fields are. There's an electron field that permeates all of space, everywhere, always. An electron isn't a thing. It's an excitation in the electron field, a ripple, a localized disturbance. Same with quarks. There's a quark field. Excitations in that field are what we call quarks, photons, excitations in the electromagnetic field. Every particle is just a vibration in a field. And fields are everywhere, overlapping, interacting. Right now, you're sitting in the electron field, the quark field, the photon field, the neutrino field, and a dozen others. You don't notice them because most of the time the fields are in their ground state. No excitations, no particles. But when there's enough energy, the field gets excited, and a particle appears. So what are you, really? You're a temporary pattern of excitations in multiple quantum fields. Your electrons are ripples in the electron field. Your quarks are ripples in the quark field. The forces holding you together are mediated by other fields. The electromagnetic field, the strong field, the weak field. You are not a collection of solid objects. You are a dynamic, shifting quantum pattern in a web of fields that fills the universe. And that pattern, for a brief moment in cosmic time, is stable enough to be aware of itself. That's you. So let's come back to where we started. You are 99.9% empty space. Your atoms are mostly nothing. Your nuclei are tiny. Your electrons are clouds of probability. You've never touched anything. You're held up by quantum forces you can't see. Most of your mass comes from energy, not matter. You're not a solid object. You're a pattern in a quantum field. And you can't even know everything about yourself because nature forbids it. So why don't you fall through the floor? Because of the Pauli exclusion principle, because of quantum mechanics, because the universe has rules that make empty space behave like it's solid. But those rules are strange, counterintuitive, beautiful, and they remind us that reality is not what it seems. The world you experience, solid, stable, predictable, is a useful illusion, a story your brain tells you to make sense of the quantum chaos underneath. But the chaos is real, and once you see it, you can't unsee it. You'll look at your hand and know this is mostly nothing. You'll touch a table and know I'm not really touching it. You'll feel the ground beneath your feet and know I'm floating. And somehow that makes existence more miraculous, not less, because you, this fragile, temporary pattern of quantum fields, are aware. You can ask these questions, you can marvel at the answers, and that to me is the most astonishing thing of all. End.